Namaste and welcome back to JEE Chemistry with Typical Monk. This is class 17, the solid state. A crystal is chemistry at its most disciplined. The same tiny box of atoms stacked over and over, filling space in perfect ranks. Learn that one box, the unit cell, and you can read the whole solid, how tightly it packs, how heavy it is, and where the little gaps hide. Today we build the cubic cells, count their atoms, weigh a crystal from its edge, and meet the defects that break the order. One idea at a time. Here is what you will learn today. First, crystalline versus amorphous solids. Second, unit cells, primitive, body-centered, and face-centered cubic, and the number Z. Third, packing efficiency, coordination number, and voids. Fourth, the density of a unit cell. And fifth, the point defects, Schottky and Frenkel, plus the drills. One idea at a time. 4 ideas. Run this entire chapter. Look at them together first. The unit cell. It is the smallest repeating box of atoms that stacked in every direction builds the whole crystal. Number atoms per cell. The atoms per cell. It is 1 for a primitive cell, 2 for body-centered cubic, and 4 for face-centered cubic. The packing efficiency. How much of the space the spheres actually fill. 74% for face-centered cubic, 68% for body-centered, 52% for simple cubic. And the density. It comes straight from the cell. Density equals Zm over a cube times Na from the edge and its contents. Now look at the picture. The cubic unit cells, body-centered against face-centered. The primitive cell. Atoms sit only at the 8 corners, and each corner is shared among 8 neighboring cells, so it counts as one whole atom. Z equals 1. Body-centered cubic. The 8 corners plus 1 atom at the very center of the cube. Z equals 2, and the coordination number is 8. Face-centered cubic. The 8 corners plus 6 atoms at the centers of the 6 faces. Z equals 4, and the coordination number is 12. The edge and the radius. In body-centered cubic, 4r equals root 3 times a, and in face-centered cubic, 4r equals root 2 times a, the link between the atomic radius and the edge. Now the working formulas, the ones the exam turns into marks. The ribbon holds the anchors, the atoms per cell, the density, and the packing. The contribution. A corner atom counts 1/8, an edge atom 1/4, a face atom 1/2, and a body center atom 1 whole. Add them up to get Z. The density. Density equals Zm over a cube times Nr, with the edge length, N the molar mass, and Nr Avogadro's number. The packing efficiency. Simple cubic fills 52%, body-centered cubic 68%, and face-centered cubic and hexagonal close packing 74%, the closest packing possible. And the voids. A face-centered lattice has 2 tetrahedral and 1 octahedral void per atom, and the radius ratio decides which one an ion fills. Let us work the G favorite. Weighing a crystal from its edge. Take a face-centered cubic metal with an edge of 4 times 10 to the minus 8 centimeters and a molar mass of 60. Find the density, taking Avogadro's number as 6 times 10 to the 23. The data. It is face-centered cubic, so Z equals 4. The edge A is 4 times 10 to the minus 8 centimeters, M is 60, and Na is 6 times 10 to the 23. The formula. Density equals Zm over a cube times Na. The volume. A cube equals bracket 4 times 10 to the minus 8, all cubed, which is 64 times 10 to the minus 24. That is 6.4 times 10 to the minus 23 cubic centimeters. Substitute. Density equals bracket 4 times 60 over bracket 6.4 times 10 to the minus 23 times 6 times 10 to the 23, which is 240 over 38.4. The answer. Density equals 6.25 grams per cubic centimeter. And the same formula, rearranged, also gives the atomic radius from the edge. Now, the picture of the gaps between the spheres, the tetrahedral and octahedral voids. A tetrahedral void. It is a gap surrounded by 4 spheres. It is the smaller of the two, with a coordination number of 4. An octahedral void It is a gap surrounded by 6 spheres. It is the larger, with a coordination number of 6. The count. In a close-packed structure, there are 2 tetrahedral voids and 1 octahedral void for every sphere. And which one fills? The radius ratio decides. A larger cation takes the octahedral void and a smaller one takes the tetrahedral. Now what JEE actually asks. 5 pointers. 1. The atoms per cell. Primitive 1, body centered 2, face centered 4, a corner counts 1, 8, a face 1/2, a body centered 1. 2. The coordination number, simple cubic 6, body centered 8, face centered 12. 3. The packing efficiency, simple cubic 52%, body centered 68, face centered and hexagonal close packing 74. 4. The density, Zm over cube times Na, and for the radius, body centered 4r equals root 3a, face centered 4r equals root 2a. And 5. The defects, a Schottky defect, a pair of ions missing, lowers the density. A Frenkel defect, an ion shifted to a void, leaves it unchanged. Now an assertion and reason drill. For each pair, are both true, and does the reason explain the assertion? First pair. Assertion, the face-centered cubic structure has the highest packing efficiency among the cubic cells. Reason, in face-centered cubic, the atoms touch along the face diagonal, filling 74% of the space. Both are true, and the reason directly explains the assertion. The answer is second pair. Assertion, a Frenkel defect lowers the density of a crystal. Reason, in a Frenkel defect, ion moves from its lattice site into an interstitial void. The reason is true, but the assertion is false. In a Frenkel defect, the ion merely shifts, so the density is unchanged. It is the Schottky defect that lowers it. The answer is D. Third pair. Assertion, a body-centered cubic cell contains 2 atoms. Reason, Avogadro's number is 6.02, 2 times 10 to the 23. Both are true, but Avogadro's number has nothing to do with counting the 2 atoms in the cell. So the reason does not explain the assertion. The answer is B. Now match each structure to its number. The atoms in a face-centered cubic cell go to 4. The coordination number of body-centered cubic goes to 8. The packing efficiency of face-centered cubic goes to 74%. And the density of a unit cell goes to Zm over a cube times Na. 4 pairs, each worth committing to memory. Now, how many of these 3 statements are correct? 1. A face-centered cubic unit cell contains 4 atoms. That is correct. 2. A Schottky defect increases the density of a crystal. That is wrong. It lowers the density because ions are missing. 3. The coordination number of a body-centered cubic structure is 8. That is correct. So the answer 2 are correct, statements 1 and 3. The trap is statement 2. A Schottky defect lowers the density. Now the 2 mistakes that quietly cost marks. The myth, a Schottky and a Frenkel defect both change the density. The truth, a Schottky defect lowers the density since ions leave the lattice, but a Frenkel defect leaves it unchanged since the ions merely shift to a void. The second myth, a corner atom counts as 1 full atom in the cell. The truth, a corner atom is shared among 8 cells, so it counts as 1/8, and a face atom counts as 1/2. Now, test yourself. Answer in your head before the reveal. That is how JEE speed is built. Here we go. Question 1. The atoms in a body-centered cubic unit cell? 2. Question 2. The atoms in a face-centered cubic unit cell? 4. Question 3. The coordination number of face-centered cubic? 12. Question 4. The packing efficiency of face-centered cubic? 74%. And question 5. Which defect lowers the density? The Schottky defect. Let us gather it all in one breath. The atoms per cell. Primitive 1, body-centered 2, face-centered 4, a corner 1/8, a face 1/2, a body-centered 1. The coordination number. Simple cubic 6, body-centered 8, face-centered 12. The packing efficiency. Simple cubic 52%, body-centered 68, face-centered and hexagonal close packing 74. The density Zm over a cube times Na, body-centered 4R, equals root 3a, face-centered 4R, equals root 2a. A Schottky defect lowers the density, a Frenkel defect leaves it unchanged. Next class, the p block, groups 13 and 14, the boron and carbon families. Read one unit cell and the whole crystal opens up. Its atom count, its packing, its density, and the tiny voids and defects that give solids their character. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time, you will crack JEE. I will see you in the next class.